Okay, quickly guys, we have a very short session today, and in this particular lesson I want us to look at Newton's third law and probably universal gravitation. But before we look at all of these complex things, I want us to quickly answer this question on Newton's second law. 17 marks. This is the most difficult section, hence I'm repeating this concept over and over again. Please let me know wherever I am losing you. Two blocks of masses 1,5 and 3,2 are connected to a light inextensible string. A 24 Newton force is applied on a system of blocks. All right, so you would see the 24 Newton there. All right. To move them up an incline which is 25 degrees to the horizontal at constant speed. Please, emphasis, constant speed. Once you see constant speed, never forget that the acceleration there is 0. As shown in the diagram below, the 1,5 block experiences a constant frictional force of 2 newtons. I'm going to put that here, all right, as it moves up the incline. State Newton's second law. That must be something you are eating in physics every single day. Please master that law. When a net force is applied on an object, the object will accelerate in the direction of the net force. With an acceleration, yes? Bonolo?
Well, sir, I've realized something between the statement and the diagram.
Sorry?
I'm not sure. The statement said it is only inclined surface which is 25 degrees. Whereas the diagram shows
20 degrees. Okay, no, it's fine. It was just an error. Which one did you guys use?
I used 20.
Okay, Gavin, do you use 20 as well?
Yes.
All right, so let's work with 20, no problem. Okay, cool. But Newton's second law, guys, you must state. Now, draw a labeled free body diagram of all the forces acting on the 1.5. Which forces do you see? Do you want to talk to me quickly? Which forces?
There is obvious gravitational force.
Oh, it's obvious.
Yeah.
Hey, this child, you are now well. I see. Give me a force. Let's distribute. Given? All right, given, how should I draw my normal force? Okay, tell me which one is correct. I'm going to number them. 1, 2, 3. Which one is correct?
2.
2. All right. Bonello? 1 is correct, given. That is a common mistake that we make. Please go back to your diagram. Look at this. We said the normal force is supposed to be perpendicular. Given, please don't forget this now, right? Given, are you here?
Yes, sir.
All right, please look at this. This is upwards. But if I turn the surface, look at the surface. If I turn it, what do you notice about the force?
It turns.
Good. Do you notice, if I turn it again this way, what do you notice about the normal force?
It turns in the opposite direction.
So that it must form an angle of what? 90 degrees to the surface. Please, that's a common mistake, and I don't want you to repeat that mistake. Are we sorted?
Yes, sir.
All right, what other force quickly?
Tension force.
Where is tension?
Going that side, the northeast.
This child. Northeast, like that.
Yes, sir.
Okay. Given.
Frictional force.
Okay, hold on. Given. What other force do you see given?
On the
Huh?
on the Only I see 3.
I will. Given, did you read the question? Look at the last statement. The 1,5 kilogram box experiences what? Read with me, Given. Given.
Yes, sir.
Can you read with me what I just underlined?
The 1,5 kilogram box experienced a conditional friction force of 2 newtons.
Constant, not conditional, constant frictional force. So how can you tell me you're seeing 3? So where is the frictional force going to be acting?
I'm not sure.
Given you, that means you didn't read your notes. You didn't read lesson 1, lesson 2, lesson 3, lesson 4. If you are not sure, then we're not going to move forward here. It means you're not reading the notes. Bonolo? Friction should oppose direction of motion. So this object is going up the plane. Friction should act down the plane. Given, we don't want to come back here. We don't want to come back, please. And that's why you see the examiner giving you its 4 marks. 1, 2, 3, and 4. 1, 2. It's very, very important. All right. Calculate the tension in the string connected. Now, I told you guys, please, we don't work with this diagram the way it is. What do I need to do? I need to change. My good learners, please, I am begging you to get this one system right. If you get it right, you will never, ever struggle with Newton's laws. The diagram we had looks like this. Normal, Fg, tension going that way, and friction. Your work starts from here. Now, we said this diagram is not good for calculation. We need to change this Fg. This is my problem. And when we change Fg, please look at what we're going to have. I have normal, I have tension, I have friction, but I want to change Fg. So I will have Fg perpendicular, which is opposite the normal force. Then I will have Fg parallel. Look at what my surface is. My surface is like this. So Fg parallel must be acting downwards and parallel to the surface. If you can do this, just this alone, I promise you, you are done with Newton's laws. Fg perpendicular, Fg parallel, and it is always, this is mg cos, you must remember this, theta, I like to use alpha, while this is mg, this is, guys, you are done with physics. If you can do this, you are done with physics. And this is the 1,5 kg. Please, is there any question you want to ask me on this? Please let me know. I don't mind repeating. Are we okay or we are lost? Please don't give me thumbs up now and then next question you start doing nonsense. Please, very, very important. Now, we are looking for tension. The object is moving horizontally upwards, right? Okay, so these are the forces that are responsible for the object's motion. The object is moving this way. Do you see that? Okay, so we are going to be working with, I have 7 minutes on this question. Come on, where's my arrow? All right. Now, this is plus, negative, and negative, because direction of motion is positive. Lovely. F net is equal to MA. Let's add all the forces. Tension is positive, friction is negative, FG parallel is negative, and that is equal to MA. I do not know tension, but I know that this is FK minus, I wrote this formula out for you, T minus 2, mass is 1,5, 9,8, sine, we used 20, right? Acceleration is 0. Why? Object is moving at constant what? Velocity. Those are things that you must not forget. We do the maths. What is tension? Move everything over to the other side. What are we going to get? 1,5 times 0 is 0. Move the 2 over, it becomes positive 2. Move that 1 over, it becomes positive 1,5, 9,8, and sine 20. And good, we are done. Simple. 7,03. Case closed. Your free body diagram is the answer. Free body. And please go back to lesson 3 and lesson 4. Very important. This I was just doing to make sure that we fix whatever needs to be fixed. Next question. Calculate the coefficient of friction between the 3,2 block and the surface. Guys, I cannot do this question without drawing the free body diagram on the 3,2. You would notice this. There is a 24 Newton force. All right, so let's draw the 3,2. Okay, we corrected. We said normal must be at the way the surface is. Normal. We have FG. We have applied force. Object is being pulled. But there's a tension force between that object and the other one. And there's also friction. That's why they told us to calculate that. So this is friction because object is moving up. Tension because the 1,5 is pulling the object. Normal, 90 degrees to the surface. Gravity, like Bonolo said, obvious. And we have what? Force applied. But what did I tell you? This force is my problem. A quick one again, similar to what we did. Normal, force applied, friction, tension. Now, FG is going to be straight where normal is coming from. And the surface is downwards. FG parallel. And my good learners, case closed. Normal, force applied, FG perpendicular, which is MG cos. Write this quickly. FG parallel, which is MG sine alpha. I have my tension, I have my friction. What are we looking for? That's the question I want us to answer. Make this big. What are we looking for? Coefficient of friction. The first thing I like to do is to write the formula for coefficient of friction to see what is missing. It's 6 marks. I'm going to move quickly. Friction, Fk is mu Kn. Please watch the step by step. That's the first thing I'm going to write. I am looking for this, but I don't even have friction. That's a big problem. Now, let's quickly deal. What is normal? Go back to your diagram. I'm going to circle my normal. My normal is this. Which force is opposite the normal? There's only one force. Oh, it means my normal force is the same as Fg perpendicular, which is mg cos the angle. Lovely. All right, so that one we can solve because we know the mass. Mass is 3,2. What is G? 9,8. So we don't have a problem with this. This we are done already with that. Good. Normal force is done. The question is, what is friction? Okay, if we are looking for friction, object is moving upwards. Let's play around that motion. Object is moving like that. Oh, so the forces that are responsible are this one: plus, minus, minus, minus. Let's work. F net is equal to MA 1 minute. Force applied, it's positive, plus negative, friction is negative there. Negative tension is negative. FG parallel is negative, and that is MA. Okay, let's break it down. Force applied minus friction minus tension minus mg sine alpha. Oh, beautiful. I think we have everything we need. Force applied is 24. I don't have friction. Tension, we got 7,03. It's the same tension. Mass, 3,2. 9,8 is my G. My angle is sine 20. Mass is 3. Acceleration again, 0. Constant velocity. Sweet. All I need to do is to move everything over. Or I can just move friction over. Do you see, if I move friction over, it becomes positive. So what do I have here? 24 minus 7,03. I don't know if that makes sense to you. Because this one already is 0. Okay. Calculator, quickly. 24 minus 7,03 minus 3,2 times 9,8 sine of which angle? 20. Done. My friction is 6. Yellow. Hello, somebody saying something there? Oh, it's Mandla that just joined. 6,244. All right, my friction. Ah, beautiful. Oops, I can come back there. Ah, beautiful. Mu K N. So 6,244 equals to mu K. What is my normal? Do you notice we sorted our normal here? 3,2, 9,8, cos of. So what do? We divide both sides by that long sum there, 3,2 times 9,8, blah, 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 blah. Okay, so let's answer. Let's answer that. We get a calculator, and then we say 6,244 divided by 3,2 times 9,8 cos 20. Case closed. 0,21. We're done. 6 marks. There's no unit for that. Please take a screenshot. Take a screenshot for me and quickly send it to the group, because I want to quickly do my other laws now. I have 28 minutes. All right, thank you very much. Good learners, please take a screenshot of this question as well. I want an answer by weekend. Please take a screenshot. I want an answer. Everyone needs to work it out and give me an answer, please. Let's check if we now understand how Newton's law works. I need us to work through. We can then fix whatever we need to fix. I'm waiting for a picture. Thank you, Bonolo. All right. My good learners, Newton's third law. Now, I did state Newton's third law the other time, but I want us to quickly go through it again and look at a few examples. We're not going to waste time on this. Newton's third law. It says that if object A exerts a force on object B, then object B will exert a force on object A, which is equal in magnitude but opposite in direction. This is key, and this is always called action and reaction pair of forces. So if object A exerts a force on object B, then object B will also exert a force on object A. And in the case of Newton's second law, that's what we're doing with tension. All right? So FA on B and FB on A, they are equal but opposite in direction. Even if the objects are together, it's possible that they are just in contact with each other. They don't have, it's not a rope, definite, not a rope, but here we are still having the force of A on B, B on A. They are equal but opposite. Equal but opposite. Example. If I have a table and I have a block, what are the pair of forces? Pair of forces. Number one, the force of the box on table and force of table on the box. And in this case, the force of the table on the box is the normal force. We are done. So the box is exerting a force on the table, and the table is also exerting a force on the box. That's all. Number two, another force. Now, the earth is pulling the object, right? So we have force of the box on the earth and force of earth on the box. And the force of, I want to put that box here. And this one here, force of earth on the box, is actually known as the weight or the gravitational force. It's known as the weight. So weight is the force of the earth on an object. Are we okay, everybody? And that's our Newton's third law. That's where tension comes in. You know, two objects are pulling each other by a rope. That's where we bring in tension. I think I have one multiple choice. Let's see. Are we done writing? Okay, let's make it fast. I want to introduce you to universal gravitation quickly. Give me a thumbs up once you're done. Mandla, are we done? Okay, Mandla, please take a screenshot for me or Given. Bonolo just logged out so she can have a note. Somebody just take a screenshot for me. I'm sure you have taken the screenshot. I'm just waiting to receive it. If you can. All right, what do you think the answer to this question would be? If a mug is placed on a table, the reaction force due to the weight of the mug, you see, the examiner says weight of the mug, according to Newton's third law, is the force of the, please answer A, B, C, or D. First, you have to know what the weight is, which is what I just gave you. The answer is in the note that you wrote. If you can define the weight, then you'll be able to answer the question. A, B, C, or D, quickly. A, B, C, or D? Come, guys, come. A, B. If you check the note, it's very straightforward. The answer is staring right at you. I need answers. We don't have time. Given says C. Given, why are you saying C though?
So I say D.
Okay, no, Given type C, Mandla, you said D. Given, what is the weight? Please look at the note. Look at number 2. Force of the box on the earth and the force of the earth on the box. And the force of the earth on the box is called the weight. It is box and earth. That's what we mean by weight. So if I say weight here, what is it? It is force of earth on the mug. Now, just go the other way. Our answer would be mug on earth. D. The notes, please take note of my notes. There are always answers in the note. Answers are always in the note. Let's take a quick introduction to the last law. Universal gravitation. We won't finish this today, but I want us to start it quickly. Now, all objects in the universe attract each other. That's what the law says. All objects in the universe attract each other. If they're attracting, there must be a force. It says the force, the magnitude of the force of attraction. The magnitude of the force of attraction is directly proportional to the product of the masses and inversely proportional, it's a long one, to the square of the distance between their centers. You have to swat this thing. The magnitude of the force of attraction between two objects is directly proportional to the product of the masses, M1 and M2. Product means we multiply. So object 1, let me do this. Object 1 and object 2. Object 1 and object 2. So we have M1, M2. The magnitude is directly proportional. Let's quickly interpret that. F is directly proportional to the product of the masses. Interesting. Directly proportional. If I have F there and I multiply M1 and M2, I'm going to have that graph. Directly proportional. And inversely proportional to, inverse means 1 over, to the square of the distance between their centers. To the square of the distance between their centers. If I have F and I have D squared, I'm going to draw two graphs for this. And this graph can be repeated and redrawn like this. I'll give you time to write very quickly. 1 over D squared. But now it would be a straight line. I want you to see the difference between the two. If it is just D squared, it is a curve. But if it is 1 over D squared, then it is a straight line. Please draw quickly. Let me know once we are done. All right, please take note. D is the distance between their centers. Please, centers. not between them. They are centers. Now, if we combine all of this together, we are going to arrive at a formula, and this is the formula. F would be equal to G M1 M2 over D squared, where F is the force of attraction measured in newtons. We are going to go through all of these variables one by one. All right. If we consider the earth and an object, then F becomes the weight, because the force between the earth and an object, just like we did under Newton's third law, the force between the earth and an object is known as the weight, and that is mg. Please take note, F is force of attraction between objects. Let's quickly add this. I know I didn't write it, just add it. Between objects measured in newtons. If we consider the earth and an object, then F becomes the weight. G is gravitational constant. All right? It's a gravitational constant of the earth, if we are dealing with the earth, that you would get from a formula page. You don't need to stress about it. We are going to pick that value from a formula page. It is a constant, so we would be picking that. It's called a universal gravitational constant. Okay. M, let me write the value for you, but we will pick it from the formula page at any given time. It's 6,67 times 10 to the power negative 11, capital G. 6,67 times 10 to the power negative 11. Don't cram it, we will just get it. Newton meter squared per kg squared. That's why I shouldn't bother cramming it. Newton meter squared per kg squared. M1, mass of object 1 measured in kilogram. M2, mass of object 2 also measured in kilogram. D is the distance between their centers, between the center of objects, between the centers of objects, and it is measured in meters. Please, our units are very, very important. Next week I'm going to do a few quick things for us, but I want to end tonight on something very, very important. Then next week we'll look at calculations and all of those. But let's end the night tonight with something very, very crucial. Let me know once you are done writing. So I've described all the variables. F is in newtons, capital N. Let's add that to it. M1, M2 are in kg. D is in meters. And don't forget, it is D squared. Thumbs up when you're done. And may somebody please, man, just please take a picture of this page again so that others can have a reference. Either Mandela or given, just a quick picture. All right, I see one part. Okay, beautiful. Thank you very much. Let me see something quickly before we look at, let me see if we can, oh, look at this. Look at this. We can actually try this quickly tonight, but I won't do the last one. Just to show you what this question looks like. Look at this. A satellite of mass 1,000 kilograms is orbiting the Earth at a distance of 200 kilometers. Already, that's a big problem. I do not work in kilometers. I have to say that K is 3 zeros. Take note of that. All right, let's do this example. State Newton's law of universal gravitation is what I gave you. Where do you start from? You start from here. All objects, you see, this is the law. You must swat this thing. All objects in the universe attract blah, 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 blah. That is 2 marks. Okay, so we are done with that. Please don't wait for exam day before you swat it. Start knowing it. Look at 5.2. Calculate the magnitude of the force that the Earth exerts on the satellite. Magnitude of the force. What are we looking for? We are looking for F. And what is F? G. Now, we can write mass of the Earth, ME, mass of the satellite, and the distance between their centers. Check that. That's my formula. G in itself is a constant. Now, somebody says, how do I weigh the Earth? The mass of the Earth is also a constant. We just do one question tonight to see how these examiners throw these things. Resources, physics. I'm going to go to a grade 11 paper. Let's just pick a random paper. Okay, that's paper 1. Ooh, my folder is empty there. Let's get this one. Okay. So you come to the formula page and get your answer. Look at the, do you see the second one? Universal gravitation, 6,67. Now, if you go down, you would see the mass of the Earth. Let me screenshot this for us so that we can work with it. I'll also show you where to get that formula from. You don't need to cram it. Look at that. There are certain things I need in this question. Why is my board lagging? All right. So I have my table of constants. Okay. And if I move down on the formula page, look at. Can you see? I'm working with forces, and this is what I am going to be working with. It's right there. There's no need to cram it. Are we okay? So we're going to go to this page. All right, my good learners. Very, very quickly, we answer that one question and we pick it up from there and finish Newton's laws in the next lesson. So we said F equals to G, since we're talking about the Earth and a satellite, all right. Now, what is G? 6,67 times 10 to the power negative 11. We're not stressing, we're just copying. Now, ME is the mass of the Earth. If you look at the constant, you would find it there. Mass of the Earth. Do you see that? 5,98 times. Don't ask me how they measured the mass of the Earth, all right? Whether they put it on a scale. 5,98 times 10 to the power 24. 5,98 times 10 to the power. All right. What about the mass of the satellite? I think we can pick that quickly from the question. It says a satellite of mass 1,000 kilogram. Do you notice we are still maintaining the kilogram, right? So we go to there, mass of that 1,000 over, oh, I forgot my square. Now, this is where the job is. Please, the distance is between the two centers. But look at what we have. I'm going to draw the diagram they gave us. They gave us the Earth and they gave us a satellite. I want something you didn't pay attention to. I am going to show you. They measured from the center to the surface. Let's go back and see. They measured from the center, do you notice, to the surface of the Earth. Look at it. Where's my highlighter? Do you see? But they started from the center here. And they told us it's 200 kilometers. That is a very, very important information. Very, very important information. Let me draw it exactly the way they have it. So they have that, all right, and from the center they gave us 200 kilometers. We said there's a problem with that 200 kilometers because we only work with meters. So what do we say? 200, that K. Okay, but if I go to the law says, just give me a few seconds. The law says that what? I want to go back to the law to show you. Look at D. D is the distance between the centers of the object. The centers. Wait, if they are saying the centers, it means I need the center of the Earth. And that is going to be a little challenge. If I say the center of the Earth, are you agreeing mathematically that that would be the radius of the Earth? Please talk to me. Does that make sense? The centers. So I already know the distance from here to here, but I need the radius. Oh, where are we going to get the radius from? Come here. Look at the last line. The radius of the 6,38 times 10 to the power 3 kilometers. We are going to have a problem. 6,38 times 10 to the power 3. So this is what? 6,38 times 10 to the power 3. Now, my distance is from the center to the center. So what is my distance going to be? I can decide to work in kilometers, then convert everything. All right, so 6,38 times 10 to the power 3 is in kilometers, plus 200. Now, everything, if I convert to meters, I'll multiply by 1,000. Please, does that make sense to you? Let me know the total distance in kilometers, but we do not work in kilometers, we work in meters. So when I say times 1,000, or if you want, this is the same thing as 63800. All right, I am moving this by 1, 2, 3. It's 0. 6,380 kilometers. But if I then convert and multiply by 1,000, I'll have 3 zeros. 1, 2, 3. This is my conversion, the last 3 zeros. Please, does that make sense to you? Let me know. If you get that, we are done with this question. We just substitute. I'm not getting a response. I want to be sure we are okay, or you want me to re-explain. We're good. Oh, sweet. Let's get a calculator then. Because that is going to be... So at the bottom here, I can actually put everything at once. All right? I can put everything at once. So I can come here and say 6,38. But I'll prefer us to do it separately though, so that you don't get confused. I want us to do it separately. So 6,380,12. I have already converted to what? Meters. 200 kilometers. I have my 3 zeros again. All what? Squared. Did that make sense? The conversion. Did the conversion make sense to you? In some other formula pages, they convert it to meters, so you need to be careful. In some other data page, they tell you 6,38. All right, so the radius of the Earth, let me just put it here for you, but you use whatever you are given, is 6,38 times 10 to the power 3 kilometers. In some others, they will tell you 6,38 times 10 to the power 6 meters. Both of them, just need to take note of the one you are using. If you are using kilometers, you need to put 3 extra zeros. All right? But basically, it's 638. Remember, 1, 2. And then you have the other values. But if you are not sure, please just use... Let's check another formula page. I just want to check something quickly with you. We are done. Just want to confirm something there quickly. Let's see in another question paper what they used or recent. Let me try 2022, and then we put it in a calculator and case closed. Done. Because I know that in the grade 12 paper, it's in meters. Let me just confirm what it is here. All right, let's see this one quickly. All right, so here as well, they gave us in kilometers. So let's work with what we have. 6,38 times 10 to the power 3. And you can use your calculator if you are not so sure. 6,38 times 10 to the power 3. And then you multiply by 6,38 times 10 to the power 3, and then you multiply by 1,000. All right, you see 638 and 4 zeros. 1, 2, 3, 4. Okay, let's finish. Calculator. 6,67 times 10 to the power negative 11 times 5,98 times 10 to the power 24 mass 1,000. Please bracket 638. 4 zeros, 1, 2, 3, 4, plus 200, 3 zeros to convert, 1, 2, 3, write nicely, put a squared, boom, we are done. 9212,45 Newton. 9212, and that is it, we are done. This is the force exerted by the, what are we looking for again? Let me just quickly. Force exerted that the Earth exerts on the satellite. All right. The force exerted by Earth on the satellite is 9212. Now, finally, my final statement. What is the force exerted by the satellite on the earth. It is the same thing. You don't need to recalculate. And why is this so? This is so because of Newton's third law. If the earth exerts a force on the satellite will I missed that word. We need to go and add it. Simultaneously exert the same force on the earth, and the force is the force is equal in magnitude but opposite in direction. So they're going to ask you, without a calculation, what is the force that the satellite is exerting on the earth? Did that make sense? The force of satellite on the earth is exactly the same as the force of satellite on the earth. They go forth and back. Please take a picture. I want to go put the word simultaneously. We will finish this up next week and do more questions, please. This is the main thing. We're just going to do some little alterations here and there and do a few more. Then we move to our next concept. I may have to call you in for an extra session. Please send me a picture of this quickly. Thank you, Gavin. Oh, great. I'm glad you were taking screenshot. But quickly, there's a word that I want to quickly put. Please, let's put that word is very important. Let's go back to that definition. A few seconds. Oh, no. It's Newton's third law, not here. Go back to that Newton's third. Yep. Did I put the word? If object A exerts a force on object B will simultaneously, please put that word. It means at the same time. Simultaneously. Please, that word is important. Simultaneously exert a force on object A, which is equal in magnitude but opposite in direction. Please, that word is very, very important. It means the forces are acting at the same time. Once you put it, we are done. On object A. Okay. I just want to make this smaller, a force on object A. And we are done. Please, that homework that was sent, let's make sure we do it. And then we'll add a few more questions to that in our next session. If there's no question, I'm done. You're good. Have a lovely evening, everybody. Okay, guys. See ya.
So, I'm going to apologize for coming late to class.
No problem. It's okay. It's okay. Oh, it happens. Don't worry, it happens. Thank you for letting me know. Apology accepted.